and we were needing to talk about the fact that um, printf is going to cause some irritation, okay? Namely, well, printf or really any function or subroutine call. Because what happens when you do a subroutine call? What happens to registers x0 through x7? Right. The subroutine is not obligated to return x0 through x7 to the state that they were before the subroutine call. Okay. And so we made this simple little loop here that was just going to count up to 5 basically, right, and just print something. Okay, whatever. Um, but we've got a little bit of an issue because what did we have on line 25 here? We've got this addition, right? What we were doing there, well, we were basically just adding 1 to our counter, right? And then re-looping. Okay. Um, so the problem with that is going to be that what happens if x2 and x1 are changed by printf? Then the add is, we're going to get just garbage, right? Okay, so what this means is that we have to kind of start to talk about uh, how do you preserve data after subroutine calls, well, before and after, okay? And there's a couple of ways to do that. One would be, well, do we have to use x1 and x2 to keep track of our counter and that sort of thing? No, there certainly are plenty of other registers, okay? Now, x0 through x7 are not obligated to be preserved, but the rest of them are, okay? So we could use other registers in place of x0 through x7, okay, uh, uh, or at least put data there temporarily. We can always put it back in x0 through x7 if we need it there for, like, well, for example, for printing, right? Because for printing, where does your stuff have to go? Well, okay, so what has to go in x0 when you're printing something? The address of the string, the format string, okay? And then if you're plopping in other data, like numbers or whatever that are being printed, then those have to go in order in X1, X2, W3, and so on, right? Okay, so you have to use those registers sometimes, but in terms of preserving the data, you could always use a different set of them. Okay, so what happened when we ran this? Okay, so let's just look at that. Um, I'm pretty sure that's right where we ended. So I called it loop 1. Okay, so what's happening here, right? It's basically in an endless loop of printing, okay? And the reason, right, is that this comparison right there, that's comparing x1 and x3, right? X3 was basically we just wanted to count up to 5 and only print something 5 times, okay? But what's happening is that on the first comparison, everything's fine. We compare 0 to 5 and we say, well, they're not the same. So well, not only are they not the same, but the third one is not, or is, um, sorry, x1 is not greater than or equal to x3, right? And so what's the opposite of being not greater than or equal to? Less than. Okay, so we know we're still less than. And if we're greater than or equal to, we know we're finished. So if we're not greater than or equal to, we know we're not finished, right? And so we continue, and it loads the address string, and then it prints, because our string was just this is a string, it prints that, okay? And what we expected to see was that this would print 5 times, okay? But as we are seeing now, it is not. It's actually printing infinitely many, and that's because when we come back from printf, all of our counters and stuff have been nuked. And for that matter, the flag registers have been nuked, and that'll become important on assignment 9, okay? So let's go through GDB on this thing and see exactly what's happening. Okay. All right, so I need to assemble this with the debugging stuff, so the G flag. Let's see, loop. Sorry, the registers X0 through X7, which amongst other things had our counter, right? So, right, we're basically just doing a for loop here. In a for loop, you've got some variable that's just counting up, and then you've got another variable that's, well, what's the top end of your counting up, right? Yeah, so, okay, so I need to compile this, or sorry, assemble this with debugging. I'm going to statically link it and throw in the debugging. Elliot Ghost 1. Hi, Professor. Sorry I skipped class yesterday. That's somebody who's in my CS101 class. So what we're doing here is probably going to be Greek to them. Okay, so statically link it. Let's see, what was it? Loop 1.0, output to loop 1. Okay, and then let's GDB it. Okay, put a breakpoint in, start running, and let's step through. Okay, so let me full screen this. All right, so what do we got? What did we load into X0, X1, and X3? We put 1, 0, and 5, okay? And 1 was going to be the number that we, misspoke. 1, 2, and 3, right? So we put 0 and 1. That's going to be basically our where we're counting up. 1 in X2 because we're adding 1 each time we loop, so we have to have that number hanging around. And then we had 5 in X3, which was sort of our top end of our counter, and I just picked 5 arbitrarily here. Okay. All right, so let's also look at the flags register, right, which is down there in CPSR. And in particular, the flags that we care about, which ones are set? The third from the bottom, the CPSR register. Carry and 0 are both set, okay? And so negative and overflow are not set because they don't appear there. Okay, so if I step this again, what was the instruction that I was about to execute? The comparison, okay? And so if I step and look at the registers again, well, now which flag is set? The N flag, which is the negative flag, right? And the N flag is relevant here because how do I tell if one number is greater than or equal to another? I mean, other than just staring at it and not being a bonehead, but like from a computer standpoint, how do we know? We subtract one from the other, okay? And so I know that the first number is less than the second number if when I subtract them, I get a negative quantity, right? I did not get I did get a negative quantity here, and that makes sense because what's our counter right now? 0, and what are we comparing it to? 5, and the last time I checked, 0 is in fact less than 5, right? Okay, so that makes sense. All right, so when we did this comparison, right, So what the branch here on, yeah, go ahead, Evan. Take it back. Oh, yeah. You mean you can't see what's going on? Sorry. In fact, let me also put this stuff out of the way and put this down. It's a document camera. So the idea is you put a book or paper or something here and it scans downwards so that you can project it. Um, that's what I used before I had a fancy iPad with a pencil. I put paper there and I just write on pen and then scan the paper with the copier later. But that was a pain, so I got an iPad, and life has been good since. Um, okay, so we just our negative flag got set. Okay, it makes sense, right? And we're now about to execute this instruction. So will the branch get executed here? No, because 0 is not greater than or equal to 5, right? Okay, so that makes sense. So we will go to the next line of our program, which is to load in the address of the format string for a print, okay? And then print. Okay, so we're about to print. We haven't printed yet, obviously. And let's look at what are the values in memory here in our registers and also our flags right before we print. Okay, so what's sitting in register 0? Okay, looks like a big random number, but what really is that? So 483028. It's the address of the format string. Okay, whatever that just happened to be. Not random, but it's not something that's going to be. It's not like 0, like, oh, it's of course it's 0. Yeah, it's not going to be some number that like looks familiar. Okay, and then registers X1, X2, and X3 were the ones that we pre-selected, right? We had 0 for our counter, we had 1 for the number that we add each time, and then we had 5 as the top limit of our counter. Okay, and then if we go, then we've got a bunch of other stuff that we weren't using. And if we drop down here to our flags register, the in flag is still set because we have not executed another flag setting instruction since the last one. Okay, so the flag setting instructions are going to stay put, or excuse me, the flags are going to stay put until there's some other instruction that modifies them, right? So what instructions modify flags? And there's a bunch of them, but what kinds of instructions are going to modify the flags? Any of the comparison instructions, okay? And there's a few different flavors of those. Okay, what else? Yeah, some of the arithmetic things. So there's add with carry, okay? That would modify the carry flag, or sorry, add S, right? Would set flags appropriately based on the result of um, the addition. There's similar versions for like subtraction, multiplication, and so on, right? Okay, so there's a bunch of the arithmetic instructions that can update the flags registers. Okay, but we have not executed any of those flag modifying instructions since we did that first comparison. So the flags are exactly as they were a minute ago. Okay, but we're about to branch into printf. Okay, and so let me step one more time. Okay, and it printed, and we're now back from the printing. Let's look at the registers now. Okay, so we would be about to execute the add instruction with X2 and X1, basically just to add 1 to our counter. Okay, but now look at the registers. Not good, right? Okay, and now why did that happen? Hmm? Yeah, why did this happen? Why did all of these register values get changed? Or maybe not all of them, but a bunch of them.
Some of that 0 through 7 is like.
Well, yeah, 0 through 7 are for parameter passing. Okay, so if you want to pass parameters to a function and return values from a function, you need to do that in registers x0 through x7, possibly also with more stuff on the stack, which we'll talk about later, if you have even more parameters. Okay, but those registers are not obligated to be preserved by a subroutine. Okay, and in fact, if we compare, let's look at this list of registers versus what it was just before we did that instruction. Okay, so just looking at the pile here, what got changed and what is preserved? So this is what we were before printf. Okay, what are we after printf? Which ones are the same and which ones have been modified? Well, clearly x0 through x7 have gotten all trashed, but look at x, let's see, 17 was 483738 and 17 is 48738. So it looks like if we go down to 12, so let's see, start with 9. What do we have at 9? 073FF. Nope, 3FF. Okay, X12 is 4. Yeah. So X12 and on have gotten are the same as what they were before. Okay. So if we want to preserve our counters, we have two options. We either need to save it in memory before we go to printf and then load it back from memory right after, or put our counter and these other numbers into some of these other registers that are going to be preserved after subroutine calls. Okay, those are the two choices basically, because you got to preserve the data somehow. And while we're on the subject of what was preserved and what got changed, look at what the flags registers are coming out of printf versus what they were right before. Yeah, so what flags were set before we printed? The N flag, the negative flag. And what flags are set after we printed? For some reason, the carry and the 0 flag. Okay, why were those set? Well, because printf, right, has to do a bunch of stuff and it has to tell when it's finished. Okay, so like it has just as much right to use the flags as any other function. Um, but it's not obligated to reset the flags to what they were before it got there. Okay, so if we want to preserve the flags for some reason, that would be up to us to do that. Okay. All right. So what modifications do you want to try here? All right. What could we do? What did we see was true about, well, say X12 on? Did they get modified by printf? No. So instead of putting our counter, our number 1, our constant, right, and our top end of our counter in registers 1, 2, and 3, why don't we put them in like 12, 13, 14, or even, let's just do this to maybe be a little careful, 20, 21, 22. Okay, so in a later pile of registers that are obligated to be preserved by subroutines. Okay, so let's make that modification and see what happens. Okay, and just before we do that though, let's step one more time because we're about to come back around, okay? And now, right before we do the comparison, we're about to compare registers 1 and 3. Well, that is definitely not what we were trying to do the comparison with, right? Because things got all jumbled up by printf, okay? So this is why this thing printed forever. And if we step, okay, actually in this case, what happened? It only printed once because if I scroll back up a little bit, on the by dumb luck, what was in X1 versus what was in X3 when we came out of printf? Yeah, the thing in X1 just so happened to be greater than what was in X3. Okay. Did that necessarily have to happen? No, of course not, right? And when I ran this the first time, for whatever reason, whatever was coming out of printf was not greater than, and so it just kept repeating forever. In this case, this particular instance of running it, for whatever reason, that number in X1 just so happens to be bigger than X3, and well, okay, it's greater than, so we terminate the loop, and in this case, the program would have only printed once. Okay, now that's still not desired behavior, obviously. Okay, and so it quits and we're done. Okay, so does that kind of make sense? Yeah? All right, so let's go back to our source, okay? And let's put instead, let's just use 20, 21, and 22 instead of 1, 2, and 3, okay? And so x1 is now x20, and x3 is now 22, and then x21 is our counter, and x20 is our counter, x21 is the number 1, and so we need to put this in x20. Okay. Okay, so all I did was renumber the registers and use a later pile instead of the parameter passing ones. Is that okay? I mean, the idea is, and we'll see if it actually works. Yes? Okay, so let me save it. All right, so let's reassemble it and relink it, and there, it does in fact print exactly 5 times. Okay, and that makes sense because it's going to print when the counter is 0, 1, 2, 3, and 4, and terminate when the counter hits 5. Okay, does that make sense? We? Okay, so yeah, so there we go. That fixes that problem, or at least this is a fix for that problem. Okay, questions, preguntas, fragens? Ooh, I've got a spam bot who I'm about to ban. Spam. And he's blocked. Want to become famous? Buy followers and viewers on. I won't say the name of the website, but yeah. Yes, okay. So, questions about what we did here, or at least this one modification to it. This isn't the only modification we could have done.
What
Okay.
situation would you need to use the 0 through 7 registers if you need, like, in which situation would it be dumb to just move to like 20, 21, 22?
So
If you need to save them.
if you need to save registers that are elsewhere, like let's say you've got something in register 1 that you realize you need to save, okay? You got two options. You can either copy it over to one of the other registers that is preserved, okay? Because you can move data from one register to another, right? That's totally okay. The other would be you put it in memory, okay, which you put it on the stack, basically. And in a sense, right, we've already done a little bit of that because what's the very first and last instruction of every one of our programs? So lines 13 and 30. Well, right, but what are we doing? We're storing two registers contents out to memory on the stack, and then at line 30, we're popping them back off the stack. Okay, so is that right? So we either have to just move it to a register that's preserved or save it to memory and then pull it back off when we need it. Okay, now the the downside to putting things in registers is, and those of you guys who did 101 with me, and so we did that Brookshire stuff, what eventually happens no matter how hard you try when you're writing some complicated program? You run out of registers, right? And you're like, well, crap, I've got these 37 things I need to keep track of, but I've only got, 16 or 32 registers or whatever the number is, right? So no matter how many registers you have, you're going to run out of them. It's just going to happen. Uh, and so then you have no choice. You have to start putting stuff into memory. Now, the downside to putting stuff into memory is what's faster, accessing data from a register or accessing data from memory? Definitely from a register, okay? And so from a performance standpoint, if you can keep everything in registers, it's going to be faster. Now, on a modern processor, this isn't as big of a deal as it might seem because when I say you're putting things into memory, what does memory look like on a computer, right? What's sort of the memory hierarchy for the processor, right? So when you say memory, what's sort of the lowest form of memory? It's preserved when the computer is powered off. Well, it's stored in binary, yeah, but what's sort of the lowest, like, what kind of data storage device preserves data when you turn it off? Yeah, a hard drive of some sort. Okay, so solid state memory or a mechanical magnetic hard drive, one of the two. Okay, if you want to get old school, you can do magnetic tape, right?
What's in the Commodore 64?
Well, the early users used magnetic tape or floppy disks. Okay. So actually, how many of you guys, I mean, maybe you're a little young for this, ever listen to music on a cassette? Yeah, okay, got a few. Um, and you had your pencil, right? Because it fit perfectly in the hole if you needed to wind up the tape, right? Um, yeah, so in the late 70s, early 80s, actually, people in home computers used blank tapes as data storage devices, right? And so there would be like a little cassette reader thing that you'd hook up to your computer and you'd hit play and it would listen and read in data and then you could write data back to it the same way you would if you were recording audio. Okay, why did it? I don't know why that happens. So anyway, yes, but point being, there's uh, data storage that's static that is preserved when you power it off. Okay, then but when we talk about storing stuff in memory, what are we really talking about here? not hard drive stuff, but rather RAM, okay? And RAM, especially nowadays, right? How much RAM is in, most of these computers sitting on the desks? Yeah, 8 or 16 gigabytes, roughly. I've got 16 in my laptop. These laptops might have anywhere from 4 to 16, depending on how old they are. Um, right, but in on the order of gigabytes. Okay, um, and that's quite a lot, right? But not nearly as much as how much is going to be on your hard drive, right? How big are hard drives nowadays, right? How much storage is in your computer? Yeah, on the order of a terabyte, probably. Uh, you know, plus or minus a little bit, but that's a lot bigger than 4 to 16 gigabytes. Okay, now within a processor, though, there's actually more memory. Okay, and this stuff is called cache, C-A-C-H-E, not cash as in like dropping fat stacks of Benjamins, right? Um, Not that any of us will ever see fat stacks of Benjamins. I don't know, unless I don't know how many of you have proclivities to go rob a bank. Maybe you will after your next tuition bill. I don't know, right? So that would be an epic freshman tutorial: how to rob a bank. Yeah. Um, Somehow I think the dean or the president might get a little nervous if we offered a class. And imagine it goes in your transcript: how to rob a bank, C minus, right? Well, guess you got caught. So, um, yeah, uh, enjoy your 25 to life. uh, so anyway, right. So processors have memory inside of them called cache, and this stuff is on the order of megabytes because it's really expensive to put memory on die on a processor. It complicates the production of the processor, which means, well, a couple things. It complicates the production of the processor, but also when when a fabrication company, right? Uh, Intel has its own fabs, Taiwan Semiconductor, right? The Samsung, right? When they're fabbing wafers of processors, if they have a wafer that's, say, got 100 die on it, then they have to test all 100. Are all 100 going to work? Hmm? Almost never, right? So the yield, okay, and this is why, well, one reason, by the way, has anybody tried to buy a PlayStation in the last year or a graphics card, right? So why are they hard to come by? Well, okay, there's the demand is all screwed up because people are buying them to mine Bitcoin, or well, really they're mining them to buy Ethereum. Mining Bitcoin with graphics cards is no longer financially viable. Um, okay, so there's an extra demand. Okay, but why isn't the supply able to catch up? Because people are certainly not mining cryptocurrency with their PlayStations. Yeah, and why are the chips in short supply? Well, they can't make them fast enough between the capacity of the fabs and the fact that they don't get 100% yield out of anything. Okay. Now, in the computing world, the fact that your fabs don't produce perfect product every time is actually okay. All right. So I'll give you a good example of this. What's the difference between a 8-core Intel processor and a 6-core Intel processor? Well, yes, the number of cores, okay. But is there a line on the factory that produces 8-core wafers and a different line on the factory that produces 6-core wafers? Not necessarily, okay. So then how do you end up with 6-core chips if you're producing 8-core chips? Exactly, okay. So you produce an 8-core chip, and let's say you test it, and 6 of the 8 cores work fine, but the other 2 don't. What do? You laser fuse those 2 bad ones off, and you sell it as a 6-core chip. Okay, why is this a good thing for a company to do? Yeah, less waste. They're able to sell, what they otherwise would have to throw in the trash can for a little bit less money than they would sell the 8-core version. Make sense? This is called binning, by the way. Why? Because processor manufacturing is a combination of voodoo and cake baking.
Effectively, there are no 6-core processors. It's just 8-core processors
that only have 6 working cores. Yeah, I mean that depends, right? So, 5 years ago, there were 6-core processors that if they only had 4 working cores, they'd sell that, right? But yeah, and this is one reason why AMD actually is doing so well with their Ryzen stuff, because so you can go and buy a 16-core chip, right? But let's say you get a 16-core Ryzen 5900X, right? What's inside there? Is it one massive chip with 16 cores on it? No, they're smart. They said, let's make chiplets and put 8 and 8 and put an IO die in between. So there's actually 3 chips in there instead of just one. Okay. And then what happens if this 8-core chiplet doesn't have all 8 working cores? Ah, well, then they sell it as the 5800X, which has 6 and 6.
This is like less cost effective, right?
No, it's actually more cost effective.
I'm saying like that would require to have an even number of like which is the accidental 6-core processors.
Yes, okay, right, but they don't market 7-core things.
I feel like they should because they should all of them just to make it more effective.
Yeah, I don't know why they don't do that. Like, if they happen to get a bunch of ones that have 7 working cores, sell a 14-core chip. I mean, at some point though, is there any more benefit in terms of having to have yet another processor box, like another unit that they have to box up separately and advertise? Anyway, I digress. Okay, so sorry. The reason I got onto this tangent, although to be honest, this is more like an arc hyperbolic cotangent. Um, Arc hyperbolic cotangent. Yeah, take calculus. Um, so okay, the reason I got into this, right, was talking about memory hierarchy, right? So when you store something to memory, like, or you're reading data from memory, the processor is reading its program, that data is actually in cache, right? And so you may not actually be modifying memory out in the RAM, but cache is a lot faster than RAM. And in fact, there are 3 levels of cache on most modern processors that are progressively faster. And every time that you get faster, there's less of it, right? Because it's more expensive to produce. So, yeah.
What's the maximum? I say it's probably speaks on storage for cache, like how many megabytes or less
Well, like the current gen Risen stuff is on the order of 30 to 50 megabytes. It depends on the model, right?
have to do to get that 30 megabytes? Like, because I mean, in normal, so we get like hundreds of 200 gigabytes of what needs
Oh, yeah. So okay, that's complicated. Um, I mean, we'd have to spend an hour talking about how processors are actually fabricated. Um, and like I said, it's a combination of voodoo and cake baking. The reason I say cake baking is because, well, okay, maybe more like wedding cake making. Because what do you do if you have a wedding cake? There's all kinds of layers and stuff, right? You got to put the buttercream on, and then you got to do the ganache, and then you got to put the little. There's another layer, and then there's a topper, and then there's a little thing with the two people getting married, right? And then there's icing that says congratulations or whatever, right? So there's a layering process that you have to do, and yeah, it's voodoo. Anyway, okay. So point being though, going out to memory is slower than working in a register. Registers are kind of the ultimate memory in the sense that they are the absolute fastest thing that you can have and work with, but you're extremely limited in how many of them you've got. Okay, does that kind of make sense? Yeah. All right. So in our case here, when we store x29 and x30 out to, we're storing them out to memory on line 13, and then back on line 30, we're picking them back up afterwards to preserve their values. Okay, so that if our program changes x29 and x30, we have a record of what it was right when our program started so that we can restore it on line 30 and kind of clean up after our mess and put our tools back. Okay, does that kind of make sense? So we could sort of emulate this line 13, line 30 kind of construction to put data onto memory, onto the stack, and pop it back off the stack when we need it, as opposed to using a different set of register numbers. Okay. However, we do so at the expense of having to write and read from memory, which is a little slower. Okay. So in this case, we didn't need to do it, but we definitely will in plenty of other instances. Okay. So does that make sense? All right. So a couple other things I want to talk about. This branching and comparison thing. Okay. So B dot condition. Right? So the GE in this case for greater than or equal to. What other condition codes are there? Okay, there's actually 16 different condition codes, which seems like more than you might need, okay, because let's think about the mathematical ones that you would definitely need. Well, equal, not equal, less than or equal to, greater than or equal to, that's only 6. Okay, so what the hell are the rest of them? Well, there's also a branch always, okay, which is equivalent to just typing B, right? So it's an unconditional branch. It gets executed always. Some instructions actually have branch never, which you might think, why the hell would you ever use such a thing? There's actually good reason in some cases. If you're really trying to be careful with timings, then you might do that. But that still leaves what, another 8 of these things? Right? And one of them, or a pair of them actually, that might be useful are BCS and BCC. Okay, BCS stands for branch on carry set, and BCC stands for, what do you think? Branch on carry clear. Okay, so what that means is if you branch on carry set, under what conditions does the branch get executed? If the carry flag is set, wouldn't that be logical? Yeah, right? Okay, and then what about BCC? When would that get executed if the carry flag was cleared? Okay, so does that make sense? Right? So branch on carry set, branch on carry clear. You have those two things, and one of them might be handy for assignment 9. Okay, but the branch instructions, right, you can't just use the branch instruction by itself, okay? Because, for example, with the carry set or carry clear, or what we had here, which is greater than or equal to, what do we have to do before a branch instruction, right? The branch instructions use the flags. And so what has to happen before a branch instruction that reads the flags? Well, the flags have to get set to something, right? Am I just speaking Greek this morning? Yes. Malate Elenaka. I almost slipped into French, you know. Parlez-vous grec ancien ce matin? Depends. If I'm reading math, I'm probably equally good in both of them. But if I'm, like, let's just say that when you're studying ancient Greek, you don't learn how to, like, hello, I would like a train ticket to Athens, please. Right? You don't learn conversational ancient Greek, or how to order at an ancient Greek restaurant.
Those are just for academic stuff.
Yeah, basically. Yeah. That's the one downside to it, right? You don't get the